Let us now turn to the indirect storage, meaning storage concepts in which the heat transfer medium and the storage medium are not identical. Let's start with the liquid storage. And here we come to the system that currently clearly dominates the market, and this is the two-tank liquid salt system in combination with parabolic trough collectors. In the parabolic trough concept, a thermal oil is heated in the solar field, and the heated thermal oil can then either release the heat directly to the water-steam cycle, or the heat can be temporarily stored in the salt storage tank. However, the operating temperature of the oil is limited to just about 400 degrees C, so the storage temperature is also limited to this temperature. Also, the salt itself is capable to handle higher temperatures. So why isn't the salt used directly in the solar field? This is because of the high crystallization point of the salt. To prevent the salt from freezing during downtime, the piping has to be kept warm all the time, or it has to be drained. Unlike in a solar tower, where the salt receiver is mounted on the top of the tower and can be easily drained in case of downtime, the piping system in the parabolic trough field is at ground level and widely distributed, so that draining of the complete field in case of downtime can only be done with great effort. Therefore, the simpler to handle oil is used in the solar field instead. This concept is very successfully deployed worldwide. In 2008, the first plant with such a storage was commissioned in Spain and has been successfully feeding electricity into the grid ever since. The power plant has a capacity of 50 megawatt and the capacity of the storage comprises 7.5 full load hours. Since then, about 40 more plants based on this concept have been built worldwide. The largest of these in Arizona with a capacity of 250 megawatts. To summarize this approach, the two-tank liquid salt storage concept is a relatively simple technology. It comprises out of two storage tanks and a heat exchanger to transfer the heat into and from the storage system. Since the salt is relatively cheap and the system technology is also not very complex, this leads to favorable overall cost. The system is also very compact, so the problem of freezing can be managed relatively easily. Overall, this leads to this concept being the most successful storage concept to date, although there are some limitations and drawbacks. The temperature is limited to about only 400 degrees C by the oil, so it is not possible to use turbines as highly efficient as in the solar tower. Also, with the indirect concept, there is a loss of temperature and thus of exergy with each heat transfer. But despite this limitation, this concept is a success story. There are currently some efforts to further develop this approach. First and foremost, there are efforts to develop this concept into a direct storage by heating the salt directly in the solar field, thus saving the oil. This would also eliminate the 400 degrees C limitation. Currently, there are several test plants in operation in Portugal, Italy and China, where this concept is under investigation. In these facilities, different freeze protection concepts during downtimes are under investigation. Then there is a development to replace the two-tank system with a one-tank stratified tank to save some of the equipment costs. And another very advanced approach is to reheat the salt electrically after it has been heated by the oil before it is stored, as can be seen in this schematic. Thus, the salt can be reheated up to 565 degrees C, leading to higher turbine efficiencies. The electricity for this should then of course come from a PV or wind power plant. Such a PV thermal hybrid power plant is currently being developed in Morocco. Now let's move on to solid-state storages. Also, they are not yet used commercially in solar power plants. There are already some large-scale demonstration projects for this kind of storage. First and foremost, there is the solar tower demonstration plant in Jülich. Here air is heated to almost 700 degrees C in the solar receiver, and then the heat is temporarily stored in a solid storage system. The storage consists of ceramic bricks with a channel structure, as you can see on the picture in the left. Through the channels, the air is passing during loading and unloading. As it is loaded, the hot air heats the bricks while cooling down itself as it passes through the channels. A temperature certification is thereby formed within the ceramic bricks. The certification profile of a loaded and empty storage can be seen in the illustration on the right. The lower cold side of the storage is still cold even when fully charged, while the areas above are already warmed up to maximum temperature. Similarly, the upper warm side never really cools down, only the layers below it. The smaller the transition area between hot and cold, the better the storage utilization. Nevertheless, this layer concept means that the storage is never completely hot or completely cold, which means that the theoretical storage capacity of the material is never completely utilized. The degree of utilization is described by the factor F. Good stratified ceramic storage systems have utilization factors of 70 to 80%. Here we see a photo of the plant in Jülich. The storage is integrated into the tower and is located relatively close below the receiver in order to reduce the flow path of the hot air as much as possible. Another concept that has been under development for many years is the concrete storage, which is used in combination with parabolic trough plants. Here a register of pipes is cast in concrete. Hot oil then flows through the pipes and transfers the heat to the concrete. The challenge here is primarily to cope with the thermal stresses. The thermal expansion during heating and cooling may lead to a separation of the contact between the pipes and the concrete and to the formation of a gap. This would cause the heat transfer coefficient to drop dramatically, and the heat then could no longer be completely transferred to the concrete or from the concrete. Therefore, a special concrete has to be used here. Several companies are working on different recipes for this special concrete mixture. The picture shown here is from a test facility with concrete storage in Cyprus. As mentioned in the beginning, sand would be a perfect medium for a solid storage, as it is unbeatable cheap and available in vast quantities, for example in deserts. This desert sand should not be confused with construction sand, which is found in rivers and along coastlines. Construction sand is a highly demanded raw material because there is a lot of construction going on our planet. Desert sand cannot be used for construction because the particles are much too smooth and they therefore adhere poorly to each other. This property makes it unusable for construction, but it is ideal as a storage medium. Storing the heat in sand is also not a problem, but the challenge is how we can transfer the heat to the sand and how to extract the heat from the sand. For this purpose, concepts are being developed with air as heat transfer medium. Here hot air flows through the sand for loading. The sand can then either be in the form of a fixed bed or, as in the concept shown in this diagram, a moving bed. Here the sand moves driven by gravity through a channel with porous walls through which the air is flowing in a cross-flow. Such a concept is currently under development at the Solar Institute Jülich. In summary, sand is a cost-effective storage medium that can store heat very well even at high temperatures. The only challenge is a good heat transfer into the sand while maintaining at the same time a low pressure loss. Research is already ongoing to evolve this concept into a direct storage system in which the sand is heated directly by concentrated solar radiation. The sand could then flow through the receiver in a kind of curtain as shown here, and by this it can be heated directly in the process. Concepts for this are being developed in both the US and Germany. Finally, I would like to introduce briefly the latent heat storage. Also, it is still a little further away from commercial application. Latent heat storage systems use not only sensible heat for storage but also phase change energy. What's interesting here is that phase change can transfer heat energy without increasing the temperature of the storage medium itself, as shown in this temperature energy diagram. Everyone is familiar with this from ice cubes, which can keep a fluid cool at approximately 0 degrees C. Without ice, the whiskey here would be warmed up relatively quickly by the environment. The ice prevents the whiskey from warming up by extracting the heat from the whiskey while melting down the ice cube at the same time. Latent heat storage can achieve very high energy densities with a very small temperature spread, and that is why this concept is so interesting and research has been done for many years. Salts are the most suitable phase change materials for this application. Pure sodium or potassium nitrate, for example, have melting points just about 300 degrees C, which is about the same as the evaporation temperature of water at 100 bar. The curves would therefore fit together very well. However, there are also salts with even higher melting temperatures as shown in this table. Unfortunately, heat transfer has proven to be a major challenge in this concept. The heat transfer through solid salt is very poor compared to liquid salt. If, for example, the storage is discharged, which means that heat is transferred from the salt to the heat transfer medium, the salt will then first crystallize on the heat transfer tube walls, and thus forming an insulation layer that prevents further heat to be exchanged between tube and liquid salt. Heat exchangers with a very elaborate fin structure are therefore being developed, which increase the complexity and the cost for such systems dramatically. Until now, this has prevented the commercial use of such systems.